Right now, the fastest object humanity has ever built is hurtling through space at 430,000 miles per hour. At this incomprehensible velocity, you could circle Earth in under 4 minutes. Yet this same spacecraft, traveling at a speed that would vaporize you instantly upon contact with anything solid, would still require over 6,000 years to reach the nearest star. Here is what will shatter everything you think you know about space travel. The distance a human could actually cross in a single lifetime is not limited by engineering or money or willpower. It is limited by a barrier woven into the fabric of reality itself. Even so, within that barrier lies a loophole so profound that it would allow you to reach places millions of light years away while aging only decades. If you want to discover exactly how far one human life can stretch across the cosmos and enjoy this type of content, then please consider liking and subscribing. It truly helps more than you know. Are you ready? Let's begin. The fastest object ever created by human hands is currently screaming through space at a velocity that defies everyday comprehension. The Parker Solar Probe, launched in 2018, has achieved speeds exceeding 430,000 miles per hour during its closest approaches to the Sun. At this velocity, the probe travels fast enough to cross the entire continental United States in under 25 seconds. It moves so quickly that standing in New York, you could blink twice, and the spacecraft would have already passed Los Angeles, continued over the Pacific Ocean, and be approaching Hawaii. This achievement represents the absolute pinnacle of human engineering. Decades of technological development, billions of dollars in investment, and the combined expertise of thousands of scientists and engineers. The Parker Solar Probe exploits a series of gravitational assists from Venus to accelerate to speeds no chemical rocket could ever achieve on its own. Each flyby steals a tiny amount of the planet's orbital energy, gradually building velocity over years of careful trajectory adjustments. The probe represents humanity's single greatest effort at moving fast through the cosmic void. To appreciate how remarkable this speed truly is, consider the entire history of human velocity achievements. For most of our existence as a species, the fastest any human could travel was roughly 25 miles per hour, the top speed of a running horse. This limit persisted for over 200,000 years of human history. By 1900, automobiles pushed past 60 miles per hour. The Wright brothers flew at 34 miles per hour in 1903. Within 60 years, test pilots broke the sound barrier at 761 miles per hour. By 1969, Apollo astronauts returning from the Moon achieved nearly 25,000 miles per hour, the fastest any human has ever traveled. The Parker Solar Probe moves 17,000 times faster than those Apollo astronauts. It travels at a velocity so extreme that no human could survive aboard it, not because of the speed itself, but because the trajectory passes close enough to the Sun to experience temperatures exceeding 2,500 degrees Fahrenheit. This is speed achieved through decades of gravitational ballet, not raw engine power. Yet even this extraordinary velocity reveals a crushing truth about our cosmic limitations. At 430,000 miles per hour, the Parker Solar Probe would require approximately 6,600 years to reach Proxima Centauri, our nearest stellar neighbour at just 4.24 light-years away. To put this in human terms, a journey beginning when the ancient Sumerians first invented writing would only now be approaching its destination. A human lifetime spans roughly 80 years. This means that travelling at humanity's current maximum speed, you could cover barely more than 1% of the distance to the closest star before your heart beat its final rhythm. The mathematics become even more disturbing when you consider what one human lifetime actually accomplishes at these record-breaking speeds. Travelling continuously at the Parker Solar Probe's peak velocity for 80 years would carry you approximately 3 trillion miles. Written out completely, that number contains 12 zeros. It sounds unimaginably vast, until you measure it against the true scale of cosmic distances. 3 trillion miles equals roughly 0.05 light years. The nearest star system sits more than 80 times farther away than what an entire human lifetime at maximum velocity could cover. You would spend your whole existence traveling and never come close to leaving our stellar neighborhood. The Oort cloud provides another sobering reference point. This frozen spherical shell of ancient comets marks the outermost boundary of our Sun's gravitational influence. It extends up to 100,000 astronomical units from the Sun, with 1 astronomical unit being the distance from Earth to the Sun, roughly 93 million miles. The Oort cloud represents the true edge of our solar system, the point where the Sun's gravity finally loses its grip and interstellar space truly begins. At humanity's current maximum speed, reaching even the inner edge of the Oort cloud would require approximately 600 years of continuous travel. An entire human lifetime at unprecedented velocities would not even escape our solar system's sphere of gravitational dominance. We would die long before leaving the Sun's extended family of orbiting debris. Our entire existence of travel would accomplish less than crossing from Manhattan to Brooklyn when measured against the true scale of even our local cosmic neighborhood. Consider the Voyager 1 spacecraft for perspective on what decades of actual space travel accomplish. This remarkable probe has traveled farther from Earth than any other human-made object in history. After more than 47 years of continuous journey through interplanetary and now interstellar space, Voyager 1 has covered approximately 15 billion miles. This distance took nearly half a century to achieve, and the probe continues adding to its record every second of every day. Voyager 1 crossed the heliopause in 2012, officially entering interstellar space. This boundary marks where the Sun's solar wind loses its battle against the pressure of interstellar medium, the thin gas and dust that fills the space between stars. Headlines proclaimed that Voyager had left the solar system. Technically true in one sense, but deeply misleading in another. The probe escaped the Sun's magnetic influence, but remains firmly within the Sun's gravitational domain. It will not pass beyond the Oort cloud for another 30,000 years. 15 billion miles sounds impressive, until you realize it represents less than 0.03% of the distance to the nearest star. If the journey to Proxima Centauri were scaled down to a cross-country road trip from New York to Los Angeles, approximately 2,800 miles of highway, Voyager 1 would have traveled roughly 100 feet in 47 years. You would still be standing in your driveway, barely past the mailbox, after half a century of continuous driving. Your neighbors would watch you age from youth to retirement while your car remained visible from their kitchen window. Here is another way to grasp this disparity. Light travels at 186,000 miles per second. In the time it took you to read this sentence, light traveled far enough to circle Earth 7 times. Voyager 1, after nearly 5 decades of travel, has covered a distance that light crosses in approximately 20 hours. The probe's 47-year journey equals less than 1 day of light travel. The 4-year journey to Proxima Centauri represents over 150,000 times more distance than Voyager has covered in nearly half a century. Voyager 1 travels at approximately 38,000 miles per hour relative to the Sun. This velocity, while extraordinary by earthly standards, reveals the vast gulf between human achievement and cosmic requirement. At this speed, the probe would need over 70,000 years to reach Proxima Centauri. When Voyager 1 finally arrives at the distance of the nearest star, assuming it survives the journey through interstellar space, the humans who launched it will have been extinct longer than our entire species has currently existed. Homo sapiens emerged roughly 300,000 years ago. Voyager would need to travel for nearly a quarter of that entire span just to reach our closest neighbor. The probe will not survive that journey. Voyager 1 carries a plutonium power source that generates electricity through radioactive decay. This power source loses approximately 4 watts per year as the plutonium depletes. By 2025, the probe will lack sufficient power to operate any scientific instruments. By 2036 it will fall silent entirely, continuing its journey as a dead artifact tumbling through the void. It will drift for tens of thousands of years, a silent monument to human ambition, never reaching any destination, never being seen again by any human eye. The fundamental problem lies in the physics of chemical propulsion. Every rocket humanity has ever launched operates on the same basic principle that carried the first Chinese fireworks into the sky over 1,000 years ago. Hot gas expelled from one end pushes the vehicle in the opposite direction. Newton's third law in elegant action. You throw mass backward, and the reaction force pushes you forward. Simple, beautiful, and devastatingly limited for the purposes of interstellar travel. Chemical rockets face an insurmountable barrier encoded in the Tsiolkovsky rocket equation. This mathematical relationship, derived by Russian scientist Konstantin Tsiolkovsky in 1903, governs the maximum velocity any rocket can achieve based on two factors. The first is the exhaust velocity of its propellant, essentially how fast the rocket can throw material out its back end. The second is the ratio between the rocket's initial mass, including all its fuel, and its final mass after burning that fuel. For chemical propellants, exhaust velocities max out around 4.5 kilometers per second. This is not an engineering limitation, awaiting a clever solution. It is a fundamental constraint imposed by the chemistry of combustion itself. When you burn hydrogen and oxygen, the most energetic chemical reaction we can practically use for rockets, the resulting steam molecules can only move so fast. The energy released by breaking and forming chemical bonds has an absolute ceiling. No amount of engineering genius can make water molecules exit a rocket nozzle faster than chemistry permits. The tyranny of the rocket equation becomes horrifyingly clear when you calculate what reaching even modest interstellar velocities would require using chemical propulsion. To accelerate a small probe weighing just 1,000 kilograms to 1% of light speed using chemical rockets, you would need a starting fuel mass exceeding the total mass of the observable universe. Not the mass of the Earth, not the mass of the Sun, not the mass of all the stars in our galaxy combined. The mass of every galaxy, every star, every planet, every atom in the entire observable cosmos would not provide enough chemical fuel to accelerate a small car to 1% of light speed. This is not hyperbole or exaggeration for dramatic effect. This is what the mathematics actually demand. The rocket equation contains an exponential function that punishes any attempt to reach high velocities with chemical propulsion. Each additional increment of speed requires not just more fuel, but exponentially more fuel. The curve rises so steeply that it quickly exceeds any physically meaningful quantity of matter. Gravity assists provide some relief from this limitation, allowing spacecraft to steal energy from planets without burning fuel. By carefully timing flybys of massive bodies, a spacecraft can exchange momentum with planets, gradually accumulating speed through gravitational interactions. The Voyager probes used this technique extensively, bouncing from Jupiter to Saturn to build the velocities that carried them toward interstellar space. The Parker Solar Probe exploits multiple Venus flybys to accelerate toward its record-breaking speeds near the Sun. The mechanics of gravity assists involve falling toward a planet, gaining speed as gravity accelerates you, then leaving on a trajectory that converts some of the planet's orbital momentum into spacecraft velocity. The planet loses an imperceptible fraction of its orbital energy, while the spacecraft gains substantial speed. Jupiter moves slightly slower around the Sun after each Voyager flyby, though the change is far too small to measure. The spacecraft gained thousands of miles per hour from each encounter, but even gravity assists have hard limits. The solar system contains only so many massive bodies positioned to provide useful acceleration. Jupiter represents our largest gravity assist resource, and spacecraft can only extract so much energy from each flyby. Each gravitational boost adds velocity at the cost of years of travel time to reach the next planetary encounter. The orbital mechanics that make gravity assists possible also constrain how much total energy you can harvest from the available planets. a spacecraft designed specifically to optimize gravity assists, bouncing between planets over decades of careful maneuvering, might eventually reach velocities approaching 150,000 miles per hour. This represents roughly 4 times Voyager's current speed, achieved through a decade or more of patient trajectory planning. Still hopelessly inadequate for interstellar travel within any human timeframe, still requiring tens of thousands of years to reach even the nearest stars. The fastest outbound velocity any spacecraft has achieved, primarily through gravity assists, belongs to New Horizons, which flew past Pluto in 2015 at approximately 36,000 miles per hour relative to the Sun. After receiving a massive boost from Jupiter in 2007, the probe raced toward the outer solar system faster than any previous outbound spacecraft. The images it returned of Pluto revealed a world far more complex and beautiful than anyone had anticipated, with nitrogen, glaciers, and mountains of water ice. Yet even this impressive velocity would require over 80,000 years to cross the distance to our nearest stellar neighbor. Ion propulsion systems offer marginal improvements over chemical rockets by dramatically increasing exhaust velocity. These engines work by ionizing a propellant, typically xenon gas, and accelerating the resulting charged particles through electric fields. The ions exit the engine at velocities 10 to 20 times higher than chemical exhaust, allowing far greater efficiency in converting propellant mass to spacecraft velocity. The Dawn spacecraft used ion propulsion to explore the asteroid belt, becoming the first mission to orbit 2 different celestial bodies beyond Earth. Its ion engines allowed maneuvers that would have been impossible for chemical rockets of similar mass. The spacecraft could change its orbit gradually over months of continuous thrust, accomplishing trajectory alterations that chemical rockets could never achieve with available fuel. Yet ion engines produce thrust so minuscule that their advantages evaporate for rapid acceleration. Dawn's ion drive generated approximately 90 millinewtons of force. To understand how small this is, hold a single sheet of paper flat on your palm. The weight of that paper pressing down equals roughly the thrust of an ion engine. This tiny force, applied continuously for years, can build significant velocity. But building that velocity requires patience measured in decades, not the days or weeks of chemical rocket burns. Even with unlimited fuel and a century of continuous operation, ion propulsion cannot approach the speeds necessary for interstellar travel within human timescales. You could run an ion engine for an entire human lifetime and still not reach velocities that would meaningfully reduce journey times to nearby stars. The technology excels at efficient maneuvering within our solar system, but offers no solution to the interstellar distance problem. Ion drives are remarkable for what they do, but what they do is not enough. Nuclear thermal rockets represent the next step up the propulsion ladder. These engines work by passing hydrogen propellant through a nuclear reactor, heating it to extreme temperatures before expelling it through a nozzle. The nuclear heat source allows the hydrogen to reach velocities roughly twice those possible with chemical combustion, effectively doubling the exhaust velocity and dramatically improving the rocket equation's cruel mathematics. NASA tested nuclear thermal rockets extensively during the NERVA program throughout the 1960s and early 1970s. Engineers conducted dozens of successful reactor tests, running nuclear engines for extended periods and demonstrating that nuclear thermal propulsion works reliably. The technology was mature enough for deployment before political and budgetary considerations ended the program in 1973. We have known how to build nuclear rockets for over 50 years, but chose not to. A nuclear thermal rocket could theoretically accelerate a spacecraft to approximately 100,000 miles per hour with reasonable fuel ratios. This velocity represents a significant improvement over chemical systems, roughly tripling what we can achieve through combustion alone. The journey time to Proxima Centauri at this speed would drop to approximately 28,000 years, still impossibly long for any individual human, still longer than recorded human civilization has existed, but progress nonetheless. Solar sails represent perhaps the most elegant propulsion concept, exploiting the radiation pressure of sunlight itself to accelerate spacecraft without carrying any fuel whatsoever. When photons strike a reflective surface, they transfer tiny amounts of momentum, pushing the surface in the direction the light was traveling. A sufficiently large and lightweight reflective sheet could harness this pressure to gradually build velocity over time. The Japanese Ikaros spacecraft demonstrated solar sail technology in 2010, successfully unfurling a 14-meter membrane and achieving measurable acceleration from sunlight alone. The probe proved that the concept works in practice, not just in theory. Light can push objects through space, and sufficiently advanced sails could exploit this effect for propulsion without carrying a single gram of fuel. Close to the Sun, where radiation intensity reaches its peak, a solar sail could theoretically accelerate at rates approaching 1% of Earth's surface gravity. This sounds impressive until you realize that maintaining this acceleration requires staying near the Sun, and the entire point of propulsion is to go somewhere else. As the sail moves away from the Sun, radiation intensity drops with the square of distance. Double your distance from the Sun, and you receive only 1/4 the radiation pressure. The acceleration that seems promising near the Sun quickly becomes negligible in the outer solar system and vanishes entirely in interstellar space. A solar sail launched from a close solar approach might reach velocities of several 100,000 miles per hour before radiation pressure becomes too weak to provide meaningful acceleration. At 500,000 miles per hour, roughly 100 times Voyager's current velocity and faster than any spacecraft has ever traveled, the journey to the nearest star would still require over 5,000 years. A human lifetime at this speed would cover approximately 350 billion miles, or about 0.6 light years. You could travel roughly 1/7 of the way to Proxima Centauri. Impressive progress. But you would still die in the void between stars, never reaching your destination. This is the devastating reality of current and near-future propulsion technology. The fastest speeds achievable through any mechanism humanity has demonstrated, tested, or could plausibly construct within the next century cannot carry a human being beyond our immediate cosmic neighborhood within their natural lifespan. Chemical rockets are fundamentally incapable. Ion engines are too weak. Nuclear thermal rockets help, but not nearly enough. Solar sails cannot accelerate large masses to sufficient velocities. We remain trapped, seemingly permanently, within a few light hours of our home world. The psychological weight of this limitation shaped early scientific attitudes toward interstellar travel. Many 20th century physicists considered travel between stars to be physically impossible for biological beings. The energy requirements seemed astronomical. The journey times exceeded any reasonable definition of practical. The cosmic radiation exposure during decades-long voyages would accumulate to lethal doses. The vast, empty distances between stars appeared designed specifically to prevent the movement of life from one stellar system to another. Some scientists concluded that the universe had imposed a kind of cosmic quarantine, trapping intelligent species on their homeworlds through the simple mechanism of distance. The speed of light created a barrier that no amount of clever engineering could overcome. We might communicate with distant civilizations through radio signals that take years or centuries to arrive, but we could never visit them. We could never shake hands with an alien, or walk on a world orbiting another sun. The cosmos seemed to forbid such adventures through the merciless mathematics of space and time. Yet hidden within the very equations that seem to imprison humanity lies a loophole so profound that it transforms everything we think we know about the relationship between distance, time, and the limits of human exploration. This loophole was discovered in 1905 by a 26-year-old patent clerk working in Bern, Switzerland. His name was Albert Einstein, and he asked a simple question that would shatter 3 centuries of assumptions about how the universe operates. Einstein wondered what would happen if you could ride alongside a beam of light. What would you see? How would time pass? What would happen to the space around you? The answers he found contradicted everything human intuition suggested about motion, time, and distance. They revealed that the barrier trapping humanity in our cosmic backyard is not nearly as solid as it appears. Distance and time, it turns out, are not the fixed quantities that everyday experience suggests. They are flexible. They stretch and compress depending on how fast you move through space. A clock aboard a speeding spacecraft does not tick at the same rate as a clock left behind on Earth. A measuring rod carried by a fast-moving traveler does not maintain the same length as an identical rod remaining stationary. The universe plays tricks with space and time that make the seemingly impossible suddenly achievable. But to understand how far a human could actually travel in one lifetime, we must first abandon our intuitive understanding of how motion works. We must enter a realm where clocks run at different rates depending on their velocity, where distances contract for speeding travelers, and where the 80-year barrier imposed by human mortality becomes something far more flexible than it appears. The universe operates according to rules that seem specifically designed to frustrate our dreams of cosmic exploration, yet those same rules contain hidden provisions that could allow a single human lifetime to span distances currently occupied only by our most distant telescopic observations. The same physics that creates the light-speed barrier also provides the mechanism to make that barrier almost irrelevant for the travelers themselves. What comes next will fundamentally alter how you think about speed, time, and the ultimate limits of human exploration. The cosmic prison we seem trapped within has a door, and physics itself holds the key. In 1905, a 26-year-old patent clerk in Bern, Switzerland, submitted a paper to the German physics journal Annalen der Physik. The paper bore an unassuming title that gave no hint of its revolutionary contents. On the electrodynamics of moving bodies contained no complex mathematics beyond algebra. It referenced almost no previous scientific literature. It was written by a man with no academic position, no laboratory, no research funding. Yet this single document would demolish 3 centuries of assumptions about how the universe operates and reveal that time itself bends to the will of velocity. Albert Einstein began with a premise so simple it seemed almost trivial. The speed of light in a vacuum remains constant for all observers, regardless of how fast those observers are moving. Whether you stand still on Earth or race through space at half the speed of light, you will always measure light traveling at exactly 186,282 miles per second. This constancy is not an engineering limitation or measurement artifact. It is woven into the fundamental structure of reality. From this single premise, Einstein derived consequences that shattered intuition. If the speed of light must remain constant for all observers, then something else must give. That something turned out to be time itself. Clocks aboard moving vessels tick slower than identical clocks remaining stationary. This effect, called time dilation, seemed absurd when first proposed. How could time, that most fundamental and universal of quantities, flow at different rates depending on how fast you moved? Yet the mathematics proved inescapable, and within decades, experiments confirmed what Einstein had derived from pure logic. Time dilation is real, it is measurable, and it transforms everything we thought we knew about the limits of human exploration. The relationship between velocity and time dilation follows a precise mathematical formula. Einstein introduced a quantity physicists call gamma, the Lorentz factor. This number tells you exactly how much time slows down at any given velocity. To calculate gamma, you divide 1 by the square root of 1 minus your velocity squared divided by the speed of light squared. The formula looks intimidating but yields numbers that change the fate of interstellar travelers. At everyday velocities, gamma barely differs from 1. A car traveling at highway speed experiences time dilation so minuscule that the most precise atomic clocks can barely detect it. An airplane passenger ages perhaps a few nanoseconds less than someone who stayed on the ground during a cross-country flight. The effect exists but carries no practical significance for terrestrial life. The magic begins when velocity climbs toward a substantial fraction of light speed. At 50% of light speed, Gamma reaches 1.15. Time aboard the spacecraft passes about 15% slower than time on Earth. 1 year of ship time corresponds to roughly 14 months of Earth time. Noticeable but not transformative. At 90% of light speed, Gamma jumps to approximately 2.3. For every year that passes aboard the speeding vessel, 2 years and 4 months pass on Earth. A 50-year journey at this velocity would see the traveller age 50 years while Earth aged 115 years. The crew would return to find their grandchildren elderly and their great-grandchildren running the world. Pushed to 99% of light speed and Gamma reaches 7.1. The transformation accelerates dramatically. 7 years pass on Earth for every year experienced by the traveller. A decade of ship time corresponds to 70 years of Earth time. A journey lasting 50 subjective years would span 355 years of Earth history. You would depart from one civilization and return to find an entirely different world. At 99.9% of light speed, Gamma exceeds 22. 22 years of Earth time compress into a single year aboard the spacecraft. The disparity has grown enormous. 50 years of travel would span 1100 years on Earth. The Roman Empire fell less than 1600 years ago. A journey of this duration would cross time spans comparable to the rise and fall of entire civilizations. The mathematics continue relentlessly as velocity approaches light speed ever more closely. At 99.99%, Gamma exceeds 70. At 99.999%, Gamma surpasses 223. At 99.9999%, Gamma climbs past 707. Each additional 9 added to the velocity pushes the time dilation factor higher by roughly a factor of 3. These numbers transform the question of interstellar travel. Consider a journey not to the nearest star, but to somewhere more distant. Vega, one of the brightest stars in our night sky, lies approximately 25 light-years from Earth. At conventional spacecraft velocities, reaching Vega would require hundreds of thousands of years. No human could survive even a tiny fraction of such a journey. But at 99% of light speed, with Gamma at 7.1, the calculation transforms completely. From Earth's perspective, the journey takes approximately 25 years and 3 months. Light speed is light speed, and you cannot exceed it. But from the traveller's perspective, time dilation compresses this duration by a factor of 7. The subjective journey. Time drops to roughly 3.5 years. You could travel to Vega, spend time exploring any planets orbiting that brilliant blue-white star, and return to Earth having aged only 7 years, while 25 years passed at home. Push velocity to 99.9% of light speed, and the numbers become even more remarkable. Gamma at 22 compresses that same 25-year journey to barely over 1 year of subjective time. You could visit Vega and return before your second birthday aboard the ship. Earth would age 50 years during a round trip, but you would age only 2. The Pleiades star cluster, that famous grouping of hot blue stars visible to the naked eye in winter skies, lies approximately 440 light-years from Earth. At conventional speeds, reaching the Pleiades would require millions of years. At 99.99% of light speed, with Gamma exceeding 70, the subjective journey, time drops to approximately 6 years. You could travel to one of the most famous star clusters in human mythology, explore multiple stellar systems within the cluster, and return having aged perhaps 15 years while Earth aged nearly 900 years. The center of our galaxy lies approximately 26,000 light-years away. A black hole containing 4 million times the mass of our Sun lurks there, surrounded by dense star clusters and violent phenomena found nowhere else in the Milky Way. At 99.999% of light speed, with Gamma exceeding 223, the subjective journey time falls to approximately 116 years. Still longer than a human lifetime, but within reach of a multi-generational crew or travelers willing to accept life extension technologies that might emerge in coming centuries. pushed to 99.9999% of light speed, with gamma exceeding 700, and the galactic center becomes reachable in approximately 37 years of ship time. A traveler could leave Earth at age 25, journey to the supermassive black hole at the heart of our galaxy, conduct observations impossible from Earth, and arrive having aged to 62. They would return to find that over 52,000 years had passed on Earth, but they themselves would have lived a normal human lifespan. The Andromeda Galaxy presents the ultimate test of relativistic travel within what we might call the local universe. At 2.5 million light-years distance, Andromeda represents the nearest major galaxy to our own. Its trillion stars form a spiral structure larger than the Milky Way, potentially harboring countless worlds and perhaps other civilizations. No conventional propulsion could ever bridge this gap within any meaningful time frame. Yet at velocities where gamma reaches 1 million, achievable only at speeds so close to light that the difference becomes almost philosophical, the subjective journey time to Andromeda drops to approximately 2.5 years. A traveler could cross the void between galaxies, explore an entirely separate island universe, and experience the journey as lasting less time than a typical doctoral program. Earth would age 2.5 million years during this journey. Human civilization would likely be unrecognizable or extinct upon return. But the traveler themselves would have aged only a few years. These calculations reveal a profound truth that Einstein's equations encode, but everyday experience obscures. The universe has not designed barriers to prevent cosmic exploration. Time dilation provides a mechanism that could carry human consciousness across distances that light itself requires millions of years to traverse. The limiting factor is not physics but engineering. The equations permit interstellar and even intergalactic travel within a human lifetime. We simply lack the technology to achieve the necessary velocities. But why do these extraordinary velocities require such extraordinary energy? The answer lies in another of Einstein's revolutionary insights, encoded in the most famous equation in physics. E equals mc squared tells us that mass and energy are equivalent interchangeable aspects of the same underlying reality. This equivalence has consequences for anything attempting to move at relativistic velocities. As an object accelerates, it gains kinetic energy. At low velocities, this energy increase follows the familiar patterns Isaac Newton described centuries ago. Doubling your velocity quadruples your kinetic energy. The relationship is straightforward and places no fundamental limits on how fast you can go, provided you have enough fuel. But as velocity approaches a significant fraction of light speed, something strange happens. The energy required to accelerate further begins climbing faster than Newton's equations predict. Much faster. The object begins behaving as though it has more mass than it started with. This effect, called relativistic mass increase, grows more pronounced as velocity increases. At 50% of light speed, an object behaves as though it has about 15% more mass than it possesses at rest. The extra energy you pump in to accelerate further seems to disappear into this mass increase. Rather than producing proportional velocity gains, at 90% of light speed, the effective mass has more than doubled. The same engine thrust that once produced rapid acceleration now yields sluggish response, as though the spacecraft had suddenly grown enormously heavy. At 99% of light speed, the effective mass has increased by a factor of 7. At 99.9%, the factor exceeds 22. Each increment of additional velocity requires not just more energy, but exponentially more energy. The relationship follows the same gamma factor that governs time dilation, but working against the traveler rather than for them. This mass increase explains why the speed of light represents an absolute barrier for any object possessing rest mass. As velocity approaches light speed, effective mass approaches infinity. Accelerating an infinite mass would require infinite energy. Since infinite energy does not exist, the final approach to light speed becomes asymptotic. You can get closer and closer, adding 9 after 9 to your velocity expressed as a percentage of light speed. but you can never quite arrive. The practical energy requirements for relativistic travel are staggering even at velocities far below this theoretical limit. Consider accelerating a small probe, massing perhaps 1,000 kilograms to 90% of light speed. The kinetic energy required exceeds 10 to the 19th joules. Written out, this number contains 20 digits. It equals the total energy output of our Sun for approximately 2 seconds, or the entire energy consumption of human civilization for roughly 1 million years, concentrated into accelerating a single small spacecraft. For a crude vessel capable of supporting human life during an interstellar journey, the mass might reach 100,000 kilograms or more. The energy requirement scales proportionally. Accelerating such a vessel to 90% of light speed would require energy equivalent to the Sun's total output for several minutes. This is not an engineering limitation awaiting a clever solution. It is a fundamental requirement imposed by the structure of space-time itself. The energy cost doubles when you remember that travelers generally want to stop when they arrive. Decelerating from 90% of light speed requires exactly as much energy as accelerating to that velocity in the first place. A round trip doubles the requirement again. A journey to Vega and back at 90% of light speed would require 4 times the energy needed for one-way acceleration, an amount exceeding the Sun's output for a quarter hour. These energy requirements explain why relativistic travel remains theoretical, despite the physics being well understood for over a century. No propulsion system humanity has ever built, tested, or seriously proposed can deliver energy on these scales. Chemical rockets fall short by a factor of billions. Nuclear fission improves the picture but remains hopelessly inadequate. Even nuclear fusion, the process that powers the Sun, struggles to provide the energy density necessary for practical relativistic propulsion. The acceleration profile for relativistic travel introduces additional constraints. Humans can tolerate continuous acceleration at 1 Earth gravity indefinitely. This feels like normal weight, allowing travelers to walk, eat, sleep, and function normally throughout the journey. Higher accelerations become uncomfortable and eventually dangerous. Sustained acceleration at 2 gravities causes fatigue and health problems. 5 gravities can cause blackouts. 10 gravities can be fatal. At 1 gravity of continuous acceleration, a spacecraft would reach 90% of light speed in approximately 11 months. The first half of this acceleration phase carries you toward your destination while building velocity. At the midpoint of your journey, you would flip the spacecraft and begin decelerating at 1 gravity, arriving at your destination with 0 relative velocity after the same duration of braking. This constant acceleration profile changes the journey time calculations. Rather than reaching high velocity quickly and coasting, you spend the entire journey either accelerating or decelerating. For short trips, this approach requires more energy than a coast phase would demand. For very long journeys, the constant acceleration approach actually saves time by maintaining thrust throughout, rather than coasting at a fixed velocity. 1 year of acceleration at 1 Earth gravity would bring a spacecraft to approximately 77% of light speed. 2 years would reach approximately 97%. 3 years would exceed 99%. The velocity gains slow as you approach light speed, with each additional year of acceleration adding smaller increments. But time dilation compensates, compressing the subjective journey time even as acceleration efficiency drops. The twin paradox emerges naturally from these relativistic considerations and deserves careful examination because it illustrates just how profoundly time dilation affects human experience. Imagine 2 identical twins, Alice and Bob. Alice boards a relativistic spacecraft and travels to a star 20 light-years distant at 90% of light speed. Bob remains on Earth. From Bob's perspective on Earth, Alice's outbound journey takes approximately 22 years. Her return journey takes another 22 years. Bob ages 44 years waiting for his twin to return, growing from a young adult to retirement age during Alice's absence. From Alice's perspective aboard the spacecraft, time dilation compresses each leg of the journey. At 90% of light speed, gamma equals approximately 2.3. Her 22-year outbound journey feels like only 9.5 years. Her return journey feels like another 9.5 years. Alice experiences only 19 years of travel, while Bob experiences 44. When Alice returns to Earth, she is 19 years older than when she left. Bob is 44 years older. The twins who were born on the same day are now separated by 25 years of biological age. Alice's hair might show the first hints of grey, while Bob's has gone completely white. Alice might still be building her career while Bob is planning retirement. This scenario troubled early critics of relativity, who argued that motion is relative. From Alice's perspective, Bob was the one moving away and then returning. Why should Alice age less rather than Bob? The resolution lies in the asymmetry of their experiences. Alice experienced acceleration when her spacecraft changed velocity. Bob experienced no acceleration. This asymmetry breaks the equivalence between their reference frames and determines who ages less. The twin paradox has been verified experimentally using precise atomic clocks. In 1971, physicists Joseph Hafele and Richard Keating flew cesium atomic clocks around the world on commercial airliners, comparing them to identical clocks that remained stationary. The flying clocks gained approximately 270 nanoseconds compared to the stationary clocks, exactly as special relativity predicted. The effect was tiny because airplane velocities are tiny compared to light speed. But the effect was real, measurable, and confirmed Einstein's century-old predictions. Time dilation creates strange possibilities for relativistic travelers beyond simple aging differences. Information from Earth could reach travelers during their journey, allowing them to receive news, entertainment, and personal messages from home. But the travelers would receive this information compressed in time. With years of Earth broadcasts arriving during months of ship time, they could watch decades of Earth history unfold during their journey. Seeing children grow to adults and adults grow old in accelerated playback. Communication in the opposite direction faces different challenges. Messages sent from the spacecraft would take years to reach Earth, and Earth's responses would take years to return. A traveler at 99% of light speed, journeying to a star 100 light-years distant, would experience the trip in approximately 14 years. But any message sent from the spacecraft 1 year into the journey would take decades to reach Earth, and Earth's reply would not arrive until long after the traveler had reached their destination. The visual experience of relativistic travel would be equally strange. Light arriving from ahead of the spacecraft becomes blue-shifted, its frequency increased by the Doppler effect created by the spacecraft's motion toward the source. Stars ahead would shift from their normal colors toward blue, then ultraviolet, then X-ray frequencies as velocity increases. The familiar constellations would become sources of invisible radiation, detectable only through specialized instruments. Light from behind the spacecraft experiences the opposite effect. Stars in the rear become red-shifted, their light stretched to longer wavelengths. They would shift from visible colors to infrared, then to radio frequencies, eventually becoming undetectable as their radiation dropped below any instrument sensitivity. Relativistic aberration further distorts the traveler's view. Light arriving from the sides of the spacecraft appears to come from ahead, compressed into a narrowing cone in the direction of travel. At 90% of light speed, this effect bunches most of the visible universe into a circle spanning roughly 60 degrees ahead of the spacecraft. At 99% of light speed, this circle shrinks to approximately 16 degrees. At even higher velocities, the entire cosmos collapses into a brilliant point of light directly ahead, with utter darkness behind. The interstellar medium presents hazards that grow more severe with increasing velocity. Space between stars is not perfectly empty. Each cubic centimeter contains approximately 1 hydrogen atom on average, along with traces of helium, heavier elements, and dust particles. At low velocities, this material poses no threat. Spacecraft pass through it like bullets through air, barely noticing its presence. At relativistic velocities, this sparse material transforms into a deadly radiation environment. Each hydrogen atom strikes the spacecraft with kinetic energy proportional to the gamma factor squared. At 90% of light speed, each hydrogen atom impact delivers energy comparable to cosmic ray particles. At 99% of light speed, the energy increases by another factor of 20. The spacecraft's forward surfaces would be bombarded by a continuous sleet of high-energy particles capable of damaging electronics, degrading materials, and penetrating biological tissue. Shielding against this radiation requires either massive physical barriers or active deflection systems. Magnetic fields could potentially sweep charged particles away from the spacecraft, though the field strengths required grow with velocity. Physical shielding adds mass that must itself be accelerated to relativistic velocities, compounding the energy requirements. Despite these formidable challenges, the physics of relativistic travel remains clear and verified. Time dilation is not a theoretical curiosity, but a measured phenomenon confirmed by decades of precision experiments. The equations permit human travel across interstellar and even intergalactic distances within a single biological lifetime. The barrier is not physics, but propulsion technology. What technologies might actually achieve the velocities necessary to exploit time dilation? What engines could deliver the stupendous energy requirements relativistic travel demands? The next chapter examines the propulsion concepts that could transform these mathematical possibilities into engineering realities, from nuclear explosions to antimatter annihilation, to beams of light pushing gossamer sails across the cosmos. The gap between current spacecraft velocities and the speeds necessary for interstellar travel within a human lifetime spans an almost incomprehensible gulf. Our fastest probes crawl through space at roughly 1/10,000th of light speed. Meaningful time dilation begins only above 10% of light speed and becomes truly transformative only above 90%. Crossing this velocity chasm requires propulsion concepts that transcend anything humanity has yet constructed, tested, or even fully designed. Consider the scale of the challenge. The Parker Solar Probe travels at approximately 0.06% of light speed during its closest solar approaches. Reaching 10% of light speed, the threshold where relativistic effects become noticeable, requires increasing velocity by a factor of roughly 170. Reaching 90% of light speed, where time dilation dramatically compresses journey times, requires a velocity increase of 1,500 times beyond our current maximum. This is not an incremental engineering improvement. This is a revolution in propulsion technology that must bridge 6 orders of magnitude. Yet humanity has conceived propulsion concepts that could potentially cross this gulf. Some require only engineering development using known physics. Others demand breakthroughs in materials science or energy production. A few push into speculative realms where the physics itself remains uncertain. Understanding these concepts reveals both the possibilities and limitations of interstellar travel within human lifetimes. Nuclear pulse propulsion represents perhaps the most audacious propulsion concept ever seriously studied by mainstream engineers. The idea emerged in the late 1950s at the General Atomics Laboratory in San Diego, where a team of brilliant physicists asked a question that seemed insane on its surface. What if you could harness nuclear explosions for spacecraft propulsion? What if instead of containing nuclear energy within a reactor, you simply detonated bombs behind your spacecraft and rode the blast waves to the stars? Project Orion, as the effort became known, attracted some of the finest scientific minds of the era. Freeman Dyson, Theodore Taylor, and dozens of other physicists and engineers devoted years to transforming this seemingly absurd concept into detailed engineering plans. They were not dreamers, spinning fantasies. They were serious scientists performing rigorous calculations and conducting actual experiments. The basic Orion concept works as follows. The spacecraft carries a large supply of nuclear explosive devices, essentially specially designed bombs. These devices are ejected one at a time from the rear of the spacecraft and detonated at a carefully calculated distance. The explosion creates a plasma fireball that expands outward in all directions. A massive pusher plate at the rear of the spacecraft absorbs the momentum from the fraction of this plasma that strikes it, pushing the vessel forward. Shock absorbers between the pusher plate and the crew compartment smooth out the violent impulses into tolerable acceleration. The Project Orion team conducted actual tests using conventional chemical explosives rather than nuclear devices. They built small models with pusher plates and detonated charges beneath them, demonstrating that the concept worked in practice. The models flew. The pusher plates survived repeated blasts. The shock absorption systems functioned as designed. Nuclear test ban treaties halted the program in 1963 before atomic detonations could be tested, but the physics had been validated. Calculations showed that Orion could achieve performance far exceeding any other propulsion concept then envisioned or since constructed. A modest Orion spacecraft using fission bombs could reach velocities of 3 to 4% of light speed. Larger designs incorporating hydrogen fusion bombs could potentially achieve 8 to 10% of light speed. The most ambitious designs, requiring engineering capabilities beyond 1960s technology, might reach 15% of light speed or higher. At 10% of light speed, the journey to Tau Ceti, a sun-like star approximately 12 light-years distant that may host potentially habitable planets, would require roughly 120 years. Still longer than a human lifetime, but within range of multi-generational missions or travelers willing to spend most of their existence in transit. Time dilation at this velocity provides minimal benefit, compressing the journey by only about 0.5%. The spacecraft would experience essentially the same duration as observers on Earth measure. The engineering challenges for nuclear pulse propulsion remain formidable, but not insurmountable. The pusher plate must survive repeated exposure to nuclear fireballs, temperatures of millions of degrees arriving in microsecond pulses thousands of times throughout the journey. Material science has advanced considerably since the 1960s, and modern composites and refractory metals could potentially meet these requirements. The shock absorption system must convert violent impulses into smooth acceleration without destroying the spacecraft or its occupants. This problem appears solvable with sufficient engineering effort. Carrying thousands of nuclear devices poses obvious dangers both during launch and throughout the journey. A catastrophic failure during Earth departure would scatter radioactive material across wide areas. An accident during flight could destroy the mission entirely. Yet, nuclear pulse propulsion requires no new physics and no materials or technologies beyond human capability. It represents the nearest term path to interstellar velocities, using concepts we understand today. A more recent study called Project Longshot, conducted by the United States Naval Academy in 1987 and 88, examined a fusion-powered variant of nuclear pulse propulsion. This design would use small fusion explosions rather than fission bombs, achieving higher efficiency and reducing the radioactive hazard. Longshot was designed to reach Barnard's star, approximately 6 light-years distant, in roughly 100 years at approximately 4.5% of light speed. The study concluded that such a mission was technically feasible, using technology that could be developed within decades. Antimatter propulsion occupies a unique position among interstellar concepts, offering energy density that dwarfs all other known fuel sources, while remaining grounded in well-understood physics. When a particle of matter contacts its antimatter counterpart, both annihilate completely, converting 100% of their combined mass into energy. This compares to nuclear fission, which converts roughly 0.1% of mass to energy, and nuclear fusion, which achieves approximately 0.7% conversion. Antimatter is roughly 140 times more energy dense than fusion, and 1,000 times more efficient than fission. A single gram of antimatter, annihilating with a gram of normal matter, releases approximately 180 trillion joules of energy. This equals the explosive yield of the Hiroshima atomic bomb. It represents the energy consumption of an average American household for 4.5 years. It could accelerate a small spacecraft to velocities that chemical rockets could never approach regardless of their fuel supply. The energy density of antimatter makes it theoretically ideal for bridging the velocity gap to relativistic speeds. An antimatter rocket would work by directing the products of matter-antimatter annihilation through a magnetic nozzle to generate thrust. When an electron meets a positron, its antimatter equivalent, both particles vanish and produce gamma rays. When a proton meets an antiproton, the annihilation creates a spray of particles called pions that can be directed magnetically. These pions subsequently decay into lighter particles, including muons, which can also be magnetically channeled before they decay into electrons and neutrinos. The exhaust velocity of an antimatter rocket approaches a significant fraction of light speed itself, vastly exceeding what any chemical, nuclear, or fusion system can achieve. This extreme exhaust velocity transforms the rocket equation that so cruelly limits chemical propulsion. With antimatter, achieving relativistic spacecraft velocities becomes mathematically plausible rather than requiring more fuel than exists in the observable universe. Consider a journey to Epsilon Eridani, a young sun-like star approximately 10.5 light-years from Earth that hosts at least one confirmed planet. At 30% of light speed, achievable with approximately 100 kilograms of antimatter for a modest probe, the journey would require roughly 35 years from Earth's perspective. Time dilation at this velocity compresses the traveler's experience to about 33 years, a modest but meaningful reduction. A human could depart Earth at age 30 and arrive at Epsilon Eridani at subjective age 63, still potentially vigorous enough to conduct exploration. Scaling up antimatter supplies enables higher velocities with correspondingly dramatic time dilation benefits. Several thousand kilograms of antimatter could theoretically accelerate a crewed vessel to 70 or 80% of light speed. At these velocities, the journey to Epsilon Eridani would still require approximately 13 to 14 years from Earth's perspective, but time dilation would compress the traveler's experience to 8 or 9 years. The same journey that once seemed to demand most of a human lifetime becomes comparable to a long but manageable expedition. The insurmountable obstacle with antimatter propulsion lies not in the physics but in the production. Antimatter does not exist naturally in significant quantities anywhere in the known universe. Every antiproton used for propulsion must be manufactured through particle accelerator collisions that require enormous energy inputs. Current global antimatter production totals perhaps 10 to 20 nanograms per year, generated primarily at facilities like CERN in Switzerland and Fermilab in the United States. To appreciate how minuscule this production rate is, consider that reaching Epsilon Eridani with 100 kilograms of antimatter would require accumulating current global production for approximately 5 billion years. The energy cost compounds this problem catastrophically. Creating antimatter through particle collisions consumes roughly 10 billion times more energy than the antimatter ultimately stores. Manufacturing enough antimatter for a single interstellar probe would require energy inputs exceeding total human civilization's power consumption for centuries or millennia. Antimatter storage presents equally daunting challenges. Antimatter annihilates instantly upon contact with normal matter, requiring containment systems that suspend the fuel in perfect vacuum using magnetic fields. The fuel must never touch the container walls, must remain stable during launch vibrations, and must survive decades of storage during interstellar transit. The longest antimatter has been successfully stored is approximately 16 hours, achieved at CERN in 2023. Scaling from 16 hours to decades represents an improvement factor of roughly 10,000. These production and storage challenges relegate antimatter propulsion to the distant future, if it ever becomes practical at all. The physics works beautifully. The engineering remains beyond any foreseeable capability. Antimatter represents a theoretical ideal against which other propulsion concepts can be measured, but not a near-term pathway to the stars. Beamed energy propulsion sidesteps the fundamental problem plaguing all rocket-based concepts. Rockets must carry their energy source with them, and that energy source has mass that must itself be accelerated. This creates a vicious cycle, where adding fuel to increase velocity also adds mass that requires yet more fuel to accelerate. Beamed energy systems break this cycle by leaving the power source at home. The concept traces back to the 1960s, when physicist Robert Forward proposed using powerful lasers to accelerate lightweight solar sails to interstellar velocities. A sail need carry no fuel at all. It accelerates by reflecting photons, gaining momentum from light itself. With sufficiently powerful lasers and sufficiently lightweight sails, velocities approaching significant fractions of light speed become theoretically achievable. Breakthrough Starshot, announced in 2016 with $100 million in initial funding from Russian billionaire Yuri Milner, represents the most serious modern effort to develop beamed energy propulsion. The project, endorsed by the late Stephen Hawking before his death, proposes using a ground-based laser array to accelerate tiny spacecraft called star chips to 20% of light speed. At this velocity, the journey to the Alpha Centauri system would require approximately 20 years. The breakthrough Starshot concept envisions a phased array of lasers with combined power output approaching 100 gigawatts, roughly equivalent to the electrical output of 100 large nuclear power plants. This array would focus on a spacecraft massing only a few grams, consisting of a reflective sail measuring perhaps 4 meters across connected to a tiny chip carrying cameras, communication systems, and navigation equipment. The intense photon pressure would accelerate this gossamer vessel from rest to 20% of light speed in approximately 10 minutes. The engineering challenges are staggering but potentially surmountable. The laser array must maintain coherent focus on a target, accelerating away at enormous rates, eventually receding to distances where light speed delays between the laser and its target stretch to seconds and then minutes. The sail must survive radiation intensities that would vaporize conventional materials, requiring advanced reflective coatings that remain speculative. The tiny star chip must contain functional scientific instruments despite massing less than a standard paperclip. Yet breakthrough Starshot offers genuine advantages over other interstellar concepts. The laser array remains on Earth, where it can be powered by terrestrial energy sources, maintained, upgraded, and reused for multiple missions. Each individual star chip costs relatively little compared to conventional spacecraft, allowing hundreds or thousands to be launched, improving the odds that at least some survive the journey and return useful data. The fatal limitation of beamed energy propulsion for human travel lies in deceleration. A laser-propelled sail accelerates by reflecting light from behind. It cannot slow down using the same mechanism because no laser exists at the destination to push back against. A breakthrough Starshot probe would flash through the Alpha Centauri system at 20% of light speed, having mere minutes to conduct observations before departing forever. For robotic probes seeking photographs, this might suffice. For human travelers wishing to stop and explore, this approach fails completely. Magnetic sails offer one potential solution to the deceleration problem. A superconducting loop generates an enormous magnetic field that interacts with charged particles in the interstellar medium or the stellar wind at the destination. This interaction creates drag that gradually slows the spacecraft. In principle, a magnetic sail could decelerate a vessel from relativistic velocities to rest over periods of months or years. The physics of magnetic sail deceleration works, but the engineering requirements grow severe at high velocities. Slowing from 20% of light speed requires dissipating enormous kinetic energy, heating the magnetic sail and any nearby components. The superconducting loops must maintain their properties despite this heating, requiring sophisticated thermal management. The interstellar medium density varies considerably along different trajectories, making deceleration profiles difficult to predict and control. Fusion propulsion represents perhaps the most realistic path to velocities where time dilation becomes meaningful for human travelers. Fusion reactions combine light atomic nuclei, typically isotopes of hydrogen, releasing energy far exceeding chemical or fission reactions. The Sun itself is a fusion reactor, combining hydrogen into helium and radiating the energy that makes life on Earth possible. Harnessing this same process for propulsion could open the stars to human exploration. The physics of fusion propulsion is well understood. When deuterium and tritium nuclei fuse, they produce helium and a high-energy neutron, releasing approximately 17.6 million electron volts of energy. This vastly exceeds the few electron volts released by chemical reactions. A fusion rocket could theoretically achieve exhaust velocities of 3 to 5% of light speed, enabling spacecraft acceleration to 10 or 15% of light speed with reasonable fuel ratios. Project Daedalus, conducted by the British Interplanetary Society from 1973 to 1978, produced the most detailed engineering study of a fusion-powered interstellar probe. The design called for a two-stage spacecraft burning pellets of deuterium and helium-3 through inertial confinement fusion. Powerful electron beams would compress fuel pellets until fusion ignited, expelling the reaction products through a magnetic nozzle. Daedalus was designed to reach Barnard's star, approximately 6 light-years distant, in approximately 50 years at a cruise velocity of 12% of light speed. The first stage would burn for 2 years, accelerating the spacecraft to 7.1% of light speed before separating. The second stage would continue acceleration for another 1.8 years, reaching final velocity before coasting to its destination. The spacecraft would be enormous by any standard, massing approximately 54,000 tons at launch, with the vast majority being fuel. It would carry no deceleration system, instead flashing through the Barnard star system at 12% of light speed while conducting observations during its brief passage. The probe would continue into interstellar space forever, its mission completed in the few days it spent traversing its target system. Project Icarus, initiated in 2009 by the British Interplanetary Society and the Tau Zero Foundation, revisited the Daedalus concept with updated physics and engineering assumptions. Icarus studies explored various fusion fuel combinations and engine configurations, generally confirming that velocities between 10 and 20% of light speed appear achievable with fusion propulsion, using technology that might be developed within the coming century. At 15% of light speed, the journey to Sirius, the brightest star in Earth's night sky at 8.6 light-years distance, would require approximately 57 years from Earth's perspective. Time dilation at this velocity compresses the traveler's experience by roughly 1%, providing minimal benefit. A human departing Earth at age 25 would arrive at Sirius at age 82, having spent essentially their entire adult life in transit. This represents survival but hardly practical interstellar travel, reaching velocities where time dilation substantially benefits travelers requires propulsion advances beyond conventional fusion concepts. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, offered an elegant theoretical solution. Instead of carrying fusion fuel, a ramjet would scoop hydrogen from the interstellar medium using enormous magnetic fields, fusing this collected material to generate continuous thrust. In principle, a Bussard ramjet could accelerate indefinitely, harvesting fuel as it traveled and limited only by relativistic mass increase as it approached light speed. The concept inspired decades of science fiction and serious scientific study. It seemed to offer a pathway to true relativistic travel without the fuel mass penalties that limit conventional rockets. Detailed calculations eventually revealed fatal problems with the ramjet concept. The interstellar medium contains approximately 1 hydrogen atom per cubic centimeter on average, far less in some regions and more in others. Collecting enough hydrogen to sustain fusion requires a magnetic scoop measuring thousands of kilometers across. But this enormous scoop interacts with the charged particles it collects, creating drag that exceeds the thrust the fusion drive can produce. The ramjet essentially creates a parachute larger than the engine can overcome. More recent analyses have shown that the concept might work in unusually dense regions of interstellar space, such as within giant molecular clouds, but fails in the typical interstellar medium. The dream of unlimited relativistic acceleration through fuel harvesting appears physically impossible with understood physics. Hybrid concepts combining multiple propulsion technologies offer potential improvements over any single approach. A spacecraft might use nuclear pulse propulsion to achieve initial velocity, then deploy a magnetic sail to decelerate at the destination. Alternatively, a laser-boosted sail could provide initial acceleration with an onboard fusion drive handling deceleration and maneuvering upon arrival. Consider a hybrid mission to the Tau Ceti system, 12 light-years distant, and hosting multiple planet candidates, including potentially habitable worlds. Initial acceleration comes from a ground-based laser array pushing against a sail attached to a fusion-powered spacecraft. The laser boosts the vessel to 15% of light speed during the first weeks of the journey. The spacecraft then coasts for approximately 80 years before igniting its fusion drive for deceleration, arriving in the Tau Ceti system with sufficient velocity reduction to enter orbit around the target star. This hybrid approach reduces the fuel mass the spacecraft must carry by handling acceleration externally, while retaining onboard capability for the deceleration that enables actual exploration rather than a brief fly-through. The total journey time of approximately 80 years remains longer than a human lifetime, but a crew departing in their 20s might survive to see arrival in their hundreds, assuming advances in medicine extend human lifespan during the coming century. More speculative propulsion concepts venture into physics that remains theoretical or entirely hypothetical. The Alcubierre warp drive, proposed by Mexican physicist Miguel Alcubierre in 1994, describes a configuration of space-time that would allow effective, faster-than-light travel without violating special relativity. The concept works by contracting space ahead of a spacecraft while expanding space behind, creating a bubble of flat space-time that surfs along a wave in the fabric of reality. Within the warp bubble, the spacecraft remains stationary relative to local space-time. No velocity limit is violated because the vessel is not actually moving through space. Instead, space itself is being manipulated to carry the vessel forward. Destinations that light would require years to reach could theoretically be accessed in arbitrary short times depending on how severely space is warped. The mathematics of the Alcubierre drive works within general relativity. The equations describe a physically consistent, if exotic, configuration of space-time, but creating this configuration requires negative energy density, a property that may not exist in nature. The most optimistic calculations suggest the energy requirements exceed the mass energy of Jupiter. More realistic estimates place the requirements beyond the mass energy of the entire observable universe. The Alcubierre drive remains fascinating mathematics, with no clear path to physical implementation. Wormholes represent another speculative pathway to interstellar travel, potentially bypassing the velocity problem entirely. These theoretical structures, permitted by general relativity, would connect distant points in spacetime through shortcuts outside normal three-dimensional space. A traveler entering one mouth of a wormhole might emerge from the other mouth light years or even billions of light years away, having traversed effectively zero distance through the wormhole interior. Stable, traversable wormholes require exotic matter with negative energy density to hold them open against gravitational collapse. Whether such exotic matter can exist remains unknown. Some quantum field theory calculations suggest that small amounts of negative energy density might be achievable through quantum effects, but whether these effects could be scaled to stabilize a macroscopic wormhole is entirely speculative. Even if wormholes could be created and stabilized, using them for interstellar travel faces additional challenges. The wormhole mouths must somehow be transported to the desired destinations in the first place. If one mouth must travel to Tau Ceti at conventional velocities before establishing a shortcut back to Earth, the initial journey still requires solving the propulsion problems wormholes were supposed to bypass. Returning to technologies grounded in well-understood physics, the realistic frontier for interstellar propulsion likely lies with advanced fusion systems, potentially augmented by beamed energy for initial acceleration. These technologies could plausibly achieve velocities of 15 to 20% of light speed within the coming century, assuming continued research and development investment. At 20% of light speed, the time dilation benefit remains modest but measurable. The gamma factor at this velocity equals approximately 1.021, meaning that 50 years of Earth time compressed to approximately 49 years of shipboard time. The traveller gains roughly 1 year over a 50-year journey, enough to notice but not enough to transform the fundamental experience of interstellar travel, achieving velocities where time dilation provides dramatic benefits. Above 50% of light speed and ideally above 90% requires propulsion advances that cannot currently be designed even on paper. The gap between 20% and 90% of light speed represents perhaps the most formidable barrier in all of propulsion physics. No known technology can bridge this gap with any plausible fuel source or energy supply. Yet the laws of physics do not prohibit relativistic travel. The equations permit velocities arbitrarily close to light speed, limited only by the energy available for acceleration. Time dilation genuinely compresses journey times for travelers, transforming cosmic distances from impossible to merely difficult. The universe has not designed barriers against interstellar exploration. It has merely set the price of admission extremely high. Whether humanity will ever develop propulsion technologies capable of achieving highly relativistic velocities remains uncertain. The engineering challenges are immense. The energy requirements exceed current capabilities by factors that boggle imagination. The timescales for development stretch across generations, demanding sustained commitment that human civilizations rarely maintain. But the physics works. The equations are clear. Given sufficient velocity, a human lifetime could span distances that light itself requires millennia or millions of years to traverse. The final chapter examines what happens when we assume perfect propulsion, when we ask not what velocities technology might achieve, but what distances physics itself permits a human lifetime to encompass. The answers reveal both the ultimate potential and the ultimate limits of human exploration within an expanding universe. Imagine a civilization so advanced that propulsion technology has become essentially perfect. Energy is unlimited. Acceleration to any desired velocity occurs at the push of a button. The engineering challenges that consume our current efforts have been solved so completely that spacecraft routinely achieve 99.9999% of light speed. What then becomes the ultimate limit on how far a human could travel in one lifetime? The answer emerges not from engineering constraints but from the structure of the universe itself. Even with godlike propulsion capabilities, cosmic geometry imposes boundaries that no technology can overcome. These boundaries are woven into the fabric of space-time, encoded in the expansion of the cosmos, and enforced by the finite age of everything that exists. They define the absolute maximum reach of any traveler, regardless of their velocity, their lifespan, or the sophistication of their civilization. Understanding these ultimate limits requires confronting the true nature of cosmic distances and the strange behavior of space on the largest scales. The universe is not a static container through which travelers move. It is a dynamic entity that stretches and grows, carrying galaxies apart like raisins in rising bread dough. This expansion creates horizons beyond which no traveler can ever venture, regardless of how fast they move or how long they live. The observable universe provides our first reference point for understanding cosmic limits. This sphere, centered on Earth and extending approximately 46.5 billion light-years in every direction, contains every photon that has had time to reach our planet since the beginning of cosmic time. Its total diameter spans roughly 93 billion light-years. Within this volume exist approximately 2 trillion galaxies, each containing hundreds of billions of stars, each potentially hosting planets where life might have emerged and evolved. This observable sphere seems to set an obvious maximum exploration range. Nothing beyond this boundary has ever been detected by any instrument humanity has built. No telescope, no radio antenna, no gravitational wave detector has ever registered a signal from beyond the observable horizon. In a very real sense, this sphere defines the totality of the universe accessible to human knowledge. Yet the observable universe is not the same as the reachable universe. The distinction matters profoundly for any traveller hoping to explore cosmic distances. Light that reaches Earth today from the most distant observable galaxies began its journey over 13 billion years ago, when the universe was young and small. During that immense travel time, cosmic expansion stretched the space between those galaxies and Earth. Objects that emitted light 13 billion years ago now reside 46 billion light-years away, carried outward by the expansion of space itself. This expansion continues today, and, disturbingly, it accelerates. In 1998, two independent research teams studying distant supernovae discovered that the universe's expansion rate is increasing over time. This acceleration, driven by a mysterious component called dark energy, that comprises approximately 68% of the universe's total energy content, means that distant galaxies recede from us faster with each passing year. The discovery earned the 2011 Nobel Prize in Physics and revolutionized our understanding of cosmic fate. Dark energy's influence creates a boundary more fundamental than the observable horizon. The Hubble sphere marks the distance at which cosmic expansion equals the speed of light. Objects at this boundary, approximately 14 billion light-years from Earth, recede from us at exactly 186,000 miles per second. Their recession velocity precisely matches the cosmic speed limit, creating a threshold with profound implications. Beyond the Hubble sphere, galaxies recede faster than light. This does not violate special relativity because the galaxies are not moving through space at superluminal velocities. Rather, space itself is expanding, carrying the galaxies along like boats on a swelling ocean. The distinction is crucial, but offers no comfort to would-be travelers. Whether carried by expanding space or moving through it, objects beyond the Hubble sphere recede faster than any signal or spacecraft could approach them. Light emitted today from galaxies just beyond the Hubble sphere faces an eternal journey with no destination. Each photon struggles toward Earth while the expanding space between source and destination grows faster than the photon can cross it. These photons will travel forever, through an ever-expanding void, never reaching any observer, never delivering their message about the distant cosmos they left behind. Yet the Hubble sphere is not the ultimate limit for travelers. Here the distinction between light and spacecraft becomes important. A photon travels at light speed from the moment of emission, never accelerating, never changing velocity. A spacecraft can accelerate continuously, potentially exceeding the local expansion rate at its current position and pushing outward into regions where even light from Earth could never reach. The cosmological event horizon defines the true boundary. This horizon, currently approximately 16 to 17 billion light-years from Earth, marks the maximum distance any signal or traveller departing today could ever reach. Given infinite time and unlimited velocity, beyond this boundary, cosmic expansion has already won. Space stretches faster than any approach velocity could overcome. Destinations beyond the event horizon are not merely difficult to reach, they are impossible to reach by any means consistent with known physics. The mathematics of the event horizon emerge from integrating the expansion history of the universe from now until the infinite future. As dark energy continues accelerating cosmic expansion, the event horizon does not remain static, it shrinks. Regions accessible today will become permanently inaccessible in the future as accelerating expansion carries them beyond the horizon. The window for cosmic exploration narrows with each passing moment. Current cosmological models suggest that within approximately 100 billion years, the event horizon will have contracted to encompass only our local group of galaxies. The Andromeda Galaxy, currently approaching us under gravitational attraction, will merge with the Milky Way long before this isolation becomes complete, but every other galaxy in the observable universe will have crossed beyond the event horizon. On even longer timescales, measured in trillions of years, the isolation becomes essentially total. Future astronomers inhabiting whatever merged galaxy descends from the Milky Way, and Andromeda will observe a universe containing only their immediate galactic home. No external galaxies will be visible. The cosmic microwave background radiation, that ancient echo of the Big Bang, will have redshifted beyond detection. Every observational signature of the Big Bang theory will have vanished. These future astronomers might never discover that other galaxies ever existed. They might develop physics and cosmology from first principles, observing only their local stellar environment, and conclude that their galaxy constitutes the entire universe. The evidence for the Big Bang, for cosmic expansion, for the 2 trillion galaxies we observe today, will have been erased by the very expansion that carries that evidence beyond observable reach. This cosmic isolation creates an urgent countdown for exploration. Every galaxy, every star cluster, every cosmic structure we might dream of visiting faces an expiration date after which it becomes permanently unreachable. The universe offers a window of opportunity for exploration. And that window is closing. Within these cosmic constraints, what distances could a human lifetime actually span? The answer requires combining the physics of time dilation with the geometry of an expanding universe. Calculating not just how far a traveler could go, but how far the destination will have moved during the journey. At 99% of light speed, a traveler maintaining that velocity for 50 years of subjective time would cross approximately 350 light years. Earth would age roughly 355 years during this journey, but the traveler's biological clock would record only 5 decades. This distance encompasses perhaps 50,000 star systems, including numerous stars similar to our Sun and many confirmed to host planets. Within 350 light-years lie stellar nurseries where new stars are being born. Ancient globular clusters containing stars older than the galactic disk, and diverse stellar types ranging from red dwarfs that will burn for trillions of years to blue giants that will explode as supernovae within millions of years. A 50-year journey at 99% of light speed would allow exploration of cosmic environments vastly different from our own solar neighborhood. Push velocity to 99.9% of light speed, and the numbers transform dramatically. The gamma factor at this velocity exceeds 22, meaning 50 years of shipboard time corresponds to over 1100 years of Earth time. During those 50 subjective years, a traveler would cross approximately 1100 light-years, encompassing millions of star systems across a volume of space containing perhaps 10 billion potentially habitable planets. The Orion Nebula, one of the most spectacular star-forming regions visible from Earth, lies approximately 1300 light-years distant. At 99.9% of light speed, a traveler could reach this cosmic nursery, witness the birth of new stellar systems, observe protoplanetary disks coalescing into worlds, and experience one of the most visually stunning phenomena in our galaxy, all within a human lifetime. They would arrive having aged 50 years, while Earth aged over a millennium. But they would arrive. At 99.99% of light speed, gamma exceeds 70. This range encompasses the Carina Nebula, a massive star-forming region, 7,500 light-years distant, reachable in roughly 107 years of ship time. It includes the Eagle Nebula, with its famous pillars of creation at 7,000 light-years, accessible in a century of subjective travel. The galactic center itself comes within theoretical reach at these velocities. The supermassive black hole Sagittarius A star, containing 4 million solar masses of collapsed matter, lies approximately 26,000 light-years from Earth. At 99.99% of light speed, a traveler could reach this cosmic monster in approximately 370 years of ship time. A multi-generational crew departing Earth when Rome was a young republic would be arriving now. Finding themselves at the gravitational heart of the galaxy, surrounded by dense star clusters and violent phenomena, found nowhere else in the Milky Way. The most extreme velocities push these calculations toward the mind-shattering. At 99.999% of light speed, gamma exceeds 223. 50 years of subjective time spans over 11,000 light-years, carrying a traveler nearly halfway to the galactic center in what feels like a long but manageable journey. At 99.9999%, gamma exceeds 707. 50 subjective years would cross 35,000 light-years, carrying a traveler past the galactic center and into the far side of the Milky Way. Consider what this means. A person could theoretically board a spacecraft, accelerate to extreme relativistic velocity, travel completely through our galaxy, emerging on the opposite side 100,000 light-years from Earth, and experience this entire journey as lasting roughly 140 years of personal time. With hypothetical life extension technologies, a single individual could traverse the entire Milky Way, visiting regions of the galaxy forever hidden from Earth-based telescopes by intervening dust and gas. Push gamma into the thousands, and intergalactic travel enters the realm of theoretical possibility. The Large Magellanic Cloud, a satellite galaxy of the Milky Way, orbits approximately 160,000 light-years distant. At gamma equal to 3,200, a traveler could reach this separate stellar system in 50 years of ship time, while Earth aged 160,000 years. The civilization that launched the traveler would have risen, flourished, and likely vanished long before the traveler's arrival. But the traveler themselves would have aged only 5 decades. The Small Magellanic Cloud at 200,000 light-years, the Sagittarius Dwarf Elliptical Galaxy at 70,000 light-years, the Ursa Minor Dwarf at 200,000 light-years, all these satellite galaxies of our Milky Way become accessible within extended human lifetimes at sufficiently extreme velocities. A traveler willing to spend a century of subjective time in transit could visit multiple dwarf galaxies, exploring stellar populations distinct from those in our own galactic disk. The Andromeda Galaxy presents the ultimate test of relativistic travel within our local cosmic neighborhood. At 2.5 million light-years distance, Andromeda is the nearest major galaxy to the Milky Way, a spiral structure larger than our own, containing approximately 1 trillion stars. Reaching Andromeda would require either impossibly long journeys at modest velocities or extreme relativistic speeds, where gamma factors reach tens of thousands. At gamma equal to 50,000, 50 years of subjective travel would span 2.5 million light-years, precisely the distance to Andromeda. A traveler departing Earth today at this velocity would arrive at Andromeda having aged 50 years while Earth aged 2.5 million years. They would emerge into an entirely separate island universe, surrounded by unfamiliar constellations, orbiting an unfamiliar galactic core, impossibly distant from anything resembling home. What would such a traveler find? Andromeda contains stellar populations both younger and older than those in the Milky Way. Its central bulge is larger and more prominent. It harbors its own supermassive black hole, estimated at 100 million solar masses, 25 times more massive than our own Sagittarius A star. The galaxy hosts dozens of satellite dwarf galaxies, many containing stellar populations and planetary systems, utterly unlike anything in our cosmic neighborhood. But the traveler could never share their discoveries with Earth. Even if they could somehow transmit signals back across 2.5 million light-years, the signals would require 2.5 million years to arrive. The civilization that launched them would have vanished into unrecoverable antiquity. The traveler would have become, in every meaningful sense, a citizen of Andromeda rather than the Milky Way. Their journey would be a one-way exile into an alien cosmos. Push gamma higher still, and the numbers become genuinely cosmological. The Virgo cluster, containing over 1,300 galaxies, approximately 54 million light-years distant, becomes theoretically accessible at gamma equal to 1,080,000. The traveler would age 50 years while Earth aged 54 million years, Dinosaurs roamed our planet more recently than the traveller's departure would seem to Earth-based observers. The Coma cluster at 320 million light-years, the Perseus cluster at 240 million light-years, the great galaxy clusters that define the large-scale structure of the cosmos, all fall within theoretical reach of a single human lifetime at gamma factors in the millions. A traveller could visit these distant cosmic cities, observe thousands of galaxies bound together by gravity, and witness the architecture of the universe on scales that Earth-based telescopes can only photograph. At the absolute extreme, where gamma approaches billions, the mathematics permits journeys spanning most of the observable universe within a single subjective lifetime. A traveller accelerating at one gravity continuously, flipping at the midpoint to decelerate, could theoretically reach the current observable horizon in approximately 45 years of ship time. They would age 45 years while the universe aged roughly 28 billion years. They would arrive at destinations that currently exist only as ancient light reaching our telescopes. Finding those destinations evolved beyond recognition across cosmic timescales. But even these extreme calculations encounter the ultimate limit imposed by cosmic expansion. The event horizon cannot be crossed, regardless of velocity. Destinations currently beyond approximately 17 billion light-years will remain forever inaccessible. Accelerating toward them merely postpones the inevitable moment when expansion carries them beyond reach. Moreover, destinations within the event horizon today may cross beyond it during long journeys. A traveller departing toward a galaxy near the current event horizon might find that cosmic expansion during their voyage pushed their destination permanently out of reach. The accessible universe shrinks even as travellers attempt to explore it. The one-way nature of extreme relativistic travel creates profound philosophical implications. Time dilation allows you to reach cosmic distances while aging minimally, but it does not allow you to return to the era you departed. Every journey becomes a journey forward through time from which no return is possible. Consider a round trip to the Pleiades star cluster at approximately 440 light-years. At 99% of light speed, the outward journey would require approximately 445 years of Earth time but only about 63 years of ship time. The return journey would add identical durations. The traveller would return to Earth having aged roughly 126 years, finding that nearly 900 years had passed on Earth. The civilization that launched them would be ancient history. Languages would have evolved beyond recognition. Political systems, cultural values, technological capabilities, everything familiar would have transformed across nearly a millennium of progress. The traveller would return as a living artifact from a vanished age, perhaps revered, perhaps studied, but certainly isolated from every human connection they had ever known. Extending round-trip distances multiplies this temporal isolation. A round trip to the galactic center at 99.99% of light speed would return a traveller to an Earth approximately 520,000 years in its future. Modern humans have existed for roughly 300,000 years. The Earth awaiting the traveller's return would be separated from their departure by more time than Homo sapiens has walked the planet. A round trip to Andromeda, if somehow possible at extreme relativistic velocities, would return a traveller to an Earth 5 million years in its future. 5 million years ago, the human lineage had not yet diverged from other great apes. Whatever beings inhabited Earth upon the traveller's return would be as different from current humans as we are from Australopithecus. These calculations reveal that relativistic travel is fundamentally different from any transportation humanity has experienced. The voyages of exploration that shaped human history, the journeys of Columbus and Magellan, of Lewis and Clark, of Apollo astronauts, all maintained connections between travellers and their homes. Letters could be exchanged. Travellers could return to families who remembered them. The fabric of human relationships survived. The separation of distance. Relativistic journeys sever those connections absolutely. A traveller departing Earth for distant stars accepts permanent exile not just from their home planet, but from their entire historical era. They become time travelers moving only forward, unable to revisit the past they abandoned. Even if they return to the same geographical location, they arrive in a foreign future that shares only physical coordinates with the world they knew. This perspective transforms the fundamental question of how far a human could travel. It is a trade-off between range and connection, between exploration and belonging, between discovery and return. Different travelers might make different choices based on what they value most. For one-way travelers willing to abandon their past forever, the theoretical maximum encompasses nearly the entire observable universe. A lifetime measured in subjective decades could span distances of billions of light years, delivering travelers to the remotest galaxies currently detectable by our most powerful instruments. The universe permits cosmic exploration on scales that would shame the imagination of science fiction writers. For round-trip travelers hoping to maintain some connection to human civilization, the practical limits fall dramatically. Returning within a few centuries of Earth time, maintaining some possibility that recognizable human society still exists, constrains exploration to perhaps a few hundred light years. This still encompasses hundreds of thousands of star systems and potentially billions of planets, but represents a tiny fraction of the galactic disk and an infinitesimal portion of cosmic totality. The most profound implication of these calculations concerns what they reveal about human significance in the cosmos. We inhabit a universe that permits exploration on scales exceeding our wildest imagination. The laws of physics do not trap us in our solar system. They offer pathways to the stars, to other galaxies, to the cosmic structures spanning billions of light years across the observable universe. The barriers we face are technological, not physical. They represent our current inability to generate the energies necessary for relativistic propulsion, not fundamental limits imposed by nature. The universe has not designed prisons for biological life. It has provided loopholes that could carry consciousness to the farthest reaches of observable reality. A single human lifetime, measured in subjective years, experienced by the traveler, could theoretically encompass journeys that would humble the gods of ancient mythology. From one tiny rock orbiting one average star in one unremarkable galaxy, a person could travel far enough to witness galactic superclusters containing thousands of galaxies, cosmic voids spanning hundreds of millions of light years, and the filamentary large-scale structure of space-time itself. Yet these same calculations reveal humanity's profound isolation. Even with perfect technology, most of the universe remains forever beyond reach. The event horizon recedes as we approach it, carried outward by the same expansion that defines our cosmic epoch. The overwhelming majority of galaxies we can observe have already crossed beyond any possibility of contact. We see their ancient light but can never touch their shores. The 2 trillion galaxies populating the observable universe represent a census of cosmic inaccessibility. Perhaps 1/1,000,000th of these, those within our local supercluster, might theoretically be reachable before expansion carries them beyond the event horizon. The rest exist only as images, light that travelled for billions of years to paint pictures on our telescopes of places we can never go. This cosmic perspective does not diminish the achievement of reaching the stars. It contextualizes that achievement within a larger framework of universal structure. Humanity could become a truly interstellar civilization, spreading across hundreds or thousands of light years, colonizing planets throughout our galactic arm, and still occupy an infinitesimal fraction of accessible space. We could become a galactic civilization spanning the entire Milky Way, and still represent a single grain of sand on an infinite beach. The question of how far a human could travel in one lifetime ultimately becomes a question about what kind of journey we are willing to undertake. The physics permits almost anything. The engineering remains our challenge to solve. But even beyond engineering, the choice of destination implies choices about identity, connection, and the meaning of exploration itself. A traveler departing for Andromeda accepts a one-way ticket to an alien cosmos. They will never see another human face that existed in their original era. They will never share their discoveries with the civilization that made their journey possible. They will become, in effect, the seed of a new human lineage planted in foreign soil, disconnected from the tree that produced them. Perhaps such travelers would find meaning in this cosmic pioneering. Perhaps the knowledge that human consciousness had spread beyond its native galaxy would justify any personal sacrifice. Perhaps the sheer wonder of witnessing Andromeda's trillion stars from within that distant system would compensate for everything left behind. Or perhaps the human spirit requires connection more than exploration. Perhaps the best destinations are those that allow return, that maintain the threads linking travelers to home, that preserve the possibility of sharing discovery with those who stayed behind. These questions have no universal answers. Different travelers will make different choices. Some will push toward the event horizon, seeking the farthest reaches accessible to human consciousness. Others will explore closer to home, balancing wonder against connection, range against return. The universe does not care which choice we make. It offers the same physics to every traveler, the same time dilation at every velocity, the same expansion rate in every direction. What we do with these cosmic parameters remains entirely our decision. You exist in a universe stretching 93 billion light-years across, containing structures so vast that light requires billions of years to traverse them. From your position on one small planet, you gaze outward at cosmic distances that would require numbers with 24 digits to express in miles. The scale exceeds not just human experience, but human cognitive capacity. We cannot truly comprehend how far the universe extends. Yet within a single lifetime, properly equipped with technologies we can imagine but not yet build, a human being could theoretically cross significant fractions of that incomprehensible expanse. The universe has not built walls around humanity. It has built highways stretching toward every horizon, highways we have not yet learned to travel, but that physics declares open to anyone who can master the necessary velocity. How far could a human actually travel in one lifetime? The answer depends on what we are willing to build, to sacrifice, to invest across generations. It depends on whether we value range over return, exploration over connection, discovery over belonging. It depends on choices that physics cannot make for us. Choices that remain fundamentally human, even when their consequences span cosmic distances. The stars are not impossibly distant. They merely wait for us to develop the means to reach them. The galaxies are not forever beyond our grasp. They require only sufficient velocity and sufficient willingness to accept the temporal consequences of the journey. Within the equations governing motion through space-time lies a promise that distances measured in millions of light-years could someday fall within the reach of a single human life. That promise is written in the mathematics of relativity, verified by a century of experiments, and waiting for the engineering that would transform theoretical possibility into practical capability. The universe invites exploration. And somewhere between the 430,000 miles per hour we have achieved, and the velocities where gamma exceeds millions, lies a threshold where human cosmic exploration transforms from fantasy into reality. The distance a human could travel in one lifetime is not ultimately limited by physics. It is limited only by our imagination, our determination, and our willingness to pay the price the universe demands for passage to the stars.